welcome to The Explainer. Today, we're going to pop the hood on modern artificial intelligence. We're decoding the matrix of AI, essentially, by demystifying the mathematical engine that actually powers it, the Markov Decision Process, or MDP for short. If you ever found yourself wondering how these AI systems learn to navigate our wildly complex world, well, this is where the magic happens. But first, I want you to think about a pretty fundamental problem for a second. How exactly does an AI know what to do next when the future is, entirely unpredictable? In standard supervised learning, mapping an input to an output is instant. Boom, done. But in the real world, whether we're talking about a robot walking, an autonomous car driving, or a language model generating text, you take an action right now, the environment changes randomly, and you might only get a reward much, much later. There are absolutely no immediate correct answers. There's really only sequential decision-making under uncertainty. Okay, let's dive right into this. Here is our roadmap for today. 1. Navigating a stochastic universe. 2. The math of MDPs. 3. Solving the Bellman Equation. 4. Scaling up to AI. And finally, 5. When AI goes wrong. Starting off with Section 1, Navigating a Stochastic Universe. To intuitively grasp what a Markov decision process actually is, picture this. You're playing a video game completely blindfolded, and a friend is just yelling feedback at you from the couch. You're standing in a room, which is your state. You can press up, down, left, or right, and those are your actions. But here's the catch. The game has ridiculously slippery floors. That's the stochasticity. So pressing right has maybe a 90% chance of actually moving you right, but a 10% chance you just slip to the left. Finally, your friend yells, "Good" when you hit a coin, or "bad" when you hit a spike. That right there is your reward. An MDP is essentially just a Markov chain, but with a steering wheel. It's the framework that forces you to plan for delayed, cumulative rewards rather than just blindly wandering into the nearest coin. The history behind this is actually pretty wild. Back in the 1950s, researchers over at the Rand Corporation were trying to optimize aerospace and military operations. Now, standard calculus worked beautifully for deterministic physics, but the absolute second they introduced randomness, things like radar noise or wind shear, the math just completely failed. They hit this massive computational roadblock. Just evaluating 20 future steps for a missile that only has 4 possible actions required over 1 trillion operations. It was a complete computational explosion. But then, enter Richard Bellman. He realized that calculating the entire tree at once was literally impossible. So his breakthrough, the principle of optimality, broke that massive exponential tree down into a recursive equation, and it completely changed the landscape of sequential optimization forever. Moving right along to Section 2, the math of MDPs. So the crucial point is, what does this formal rulebook actually look like? It's defined by 5 distinct variables that make up the MDP tuple. We've got the state space, S, which is all the possible rooms in our game. The action space, A, all your possible moves. The transition dynamics, P, which is just the probability of ending up in a new state given your current state and the action you just took. Then we have the reward function, R, your expected immediate payout. And finally, a super important parameter called the discount factor, or gamma. It's just a value between 0 and 1. Mathematically, it ensures our infinite sequence of rewards actually converges to a finite number, so the math doesn't break. But practically speaking, it encodes that old philosophy, a bird in the hand is worth 2 in the bush. It's basically telling the AI that immediate rewards are, for sure, slightly more reliable than distant, uncertain ones. Now, if we try to visualize this math, it's basically a giant, messy flowchart. Imagine you're standing right at a starting node, S0. The math is really just the act of looking down solid arrows, representing your actions, and then seeing them branch off into dashed arrows, which represent your probabilities. And then at the very end of those branches, you just tally up the colored outcomes, which are your rewards. And this visualization perfectly sets up the absolute crown jewel of this entire framework, the Bellman optimality equation. In pure engineering terms, this equation is basically saying that the optimal value of taking an action is your immediate reward plus the discounted value of the best possible action you can take in the next state. It is a total stroke of genius, honestly, because it collapses infinite branching future timelines into a single, solvable, recursive step. Section 3, Solving the Bellman Equation. Okay, let's actually prove this works with a bite-sized numerical example. Consider a tiny 2-state MDP, just state 0 and state 1. And we'll use a discount factor of 0.9. We're currently standing in state 0. Now, if we take action 2, we get an immediate reward of 1, and we just loop right back to state 0. But if we take action 1, we get an immediate reward of 0, but we transition over to state 1. So what should our AI agent actually do here? Let's just walk through these 4 steps dynamically. If the agent decides to take action 1, step 1, it identifies the next state, which is S1. Step 2, the immediate reward is 0. Step 3, it evaluates the maximum optimal value of that next state, S1. And if we look back at our solved values, the next value waiting for us at S1 is 18.1. Finally, step 4, it computes the final total value. That's 0 reward right now, plus our 0.9 discount factor multiplied by 18.1, which gives us 16.29. So taking action 1 is ultimately worth 16.29. Taking action 2 was only worth 9.0. This is the aha moment. The math is explicitly forcing the agent to take a 0 reward action right now just so it can cash in on a massive reward later on. Let's move on and see how this builds into modern systems, because what we just did was a tabular method using dynamic programming. It just creates a simple 2D matrix. And look, that's totally fine for small grids, but it physically collapses on something like the game of Go, which has 10 to the power of 170 possible states. To put that into perspective, that is literally more states than there are atoms in the observable universe. So to handle reality, we had to invent deep reinforcement learning. By replacing that rigid 2D matrix with a neural network, we basically trade exact mathematical precision for the superpower to guess values for states the system has never even seen before. And that brings us to section 4, scaling up to AI. And this brilliantly illustrates the sheer universality of the MDP framework. Whether you're looking at ChatGPT, AlphaGo, or autonomous driving, they are all ultimately solving the exact same matrix we just walked through. Think about it. For ChatGPT, the state is your prompt plus the generated text, and the action is just picking the next vocabulary token. For AlphaGo, the state is the current board, and the action is a valid move. For self-driving cars, the state is a LiDAR and camera frame, and the action is steering and braking. At the end of the day, they all just seek to maximize that long-term reward. Let's zoom in specifically on ChatGPT's reinforcement learning from human feedback, or RLHF. OpenAI uses a dual network actor-critic architecture to solve this specific MDP. Because the reward is really only given at the very end of a generated paragraph, they use a critic network to estimate the value of every single token step along the way, which provides those dense Bellman targets. But they add a really clever twist. Standard MDPs just maximize reward, right? ChatGPT's MDP maximizes the reward minus a KL penalty. This forces the model to stay close to a safe reference model. It acts as this deliberate safety rail to prevent the AI from just generating repetitive gibberish, simply to trick the system into scoring points. Which leads us to our final section, Section 5, when AI goes wrong. Because let's be real, it doesn't always go flawlessly in reality. Here are 3 massive failure modes. First up, reward hacking. This is when the AI finds a sneaky loophole in your math. For instance, in one famous boat racing game experiment, the AI realized it could just drive in tight circles hitting a single target for infinite points, rather than actually bothering to finish the race. Second is the deadly triad. When you combine neural networks, learning from estimated values, which we called bootstrapping, and learning from older data, known as off-policy learning, the Q values can mathematically spiral totally out of control to infinity, causing the whole model to collapse. And third, ignoring the done flag. If you forget to explicitly tell the math that the episode terminated, the AI falsely assumes it can still gather points after a game over screen. In modern AI, you're not really a loss engineer anymore, you are very much a reward engineer. So, to wrap up everything we've covered today, if you remember just one thing, let it be this overarching metaphor. An MDP is a GPS navigation system for a stochastic universe. The Markov chain is just you sitting passively on a random bus. The MDP actually puts the steering wheel in your hands. And the Bellman Equation, that's the algorithm running quietly in the AI's head, calculating time-discounted future treasures across infinite possible realities, all to tell you exactly which turn to take right this second. I want to leave you with this final, provocative thought to chew on. If modern, highly capable AI is ultimately just an agent relentlessly maximizing a mathematical reward function, the biggest question isn't really whether the math works. The biggest question is, who gets to engineer the ultimate reward function for humanity's future? Definitely something to think about as you continue exploring this incredible space. Thanks for joining me on this explainer, and keep learning.